Welcome back to the deep dive. We always try to bring you to the cutting edge of tech and explore things that are going to reshape how we live and work.
Exactly.
Well, today we are diving into something that is really mind-bending, the potential for using natural language, the way we humans talk and write every day, to actually design the chips that power everything around us.
That's right. Hardware.
We're talking about natural language processing, or NLP, and how it could revolutionize the world of hardware description languages. Those are HDLs like Verilog and VHDL. And you sent in a report that really gets into the nitty-gritty of this. So today we're on a mission to break it all down. What are the big leaps forward that could really change the game? What are the hurdles we've got to overcome? And what are those key, aha moments for anyone who wants to quickly grasp this complex topic, which, let's be honest, is kind of a mouthful.
Right.
So let's jump right in. First things first, for anyone who isn't already living and breathing this stuff, we need to make sure we're all on the same page about what HDLs actually are. So these are languages like Verilog and VHDL. They are essentially the blueprints for designing the electronic circuits that make up computer chips.
Yeah. Think of them as code, but instead of telling a program what to do, they describe the actual physical structure and behavior of the hardware itself.
Right. And these HDLs are used to design all sorts of things, like super specialized chips called ASICs, which stands for Application-Specific Integrated Circuits. These are chips that are custom designed for a very specific task, like, say, processing images in a digital camera or handling the really complex calculations in a self-driving car.
Exactly. And they're also used for programming FPGAs, field programmable gate arrays.
Oh, FPGAs, yeah. Those are amazing. They're like reconfigurable chips that can be reprogrammed to perform different functions on the fly. So you find these chips in all kinds of applications, everything from your smartphone and your laptop to massive data centers, aerospace systems, medical devices, you name it. They're absolutely critical for creating the digital world we live in.
Right. Now, what you have to understand about HDLs is that they're incredibly precise. They offer a textual way to describe circuits with no room for ambiguity.
Right.
So it's a bit like programming languages in that sense. But there is a crucial difference, the element of time.
Time.
Yes. HDLs are designed to model how a circuit behaves over time. This is crucial for simulation, essentially a virtual test run of your circuit, and ensuring everything is synchronized perfectly. And this rigor is what allows for automated analysis, virtual prototyping, all of that. But it also makes them quite demanding to learn and use.
So they're very powerful, very precise, but not exactly known for being user-friendly, and this is where NLP comes in.
Right, the idea.
Because it's all about bridging the gap between how we humans communicate, which is messy, it's fluid, it's full of nuance and context, and the very structured, very rule-driven world of these HDLs. So what's the potential here? Well, imagine being able to describe what you want a piece of hardware to do, not in lines of code, but in plain English.
Right, imagine speaking your hardware design into existence.
And then boom, the underlying code is generated automatically. I mean, this could be huge. It could open up hardware design to a much wider range of people, potentially leading to faster innovation, getting from idea to a working prototype much faster. It could also lead to more efficient, more optimized designs.
Absolutely. And, when we talk about making HDLs more accessible, it's not just about making things easier for engineers. It's about breaking down barriers between disciplines. Imagine someone with deep expertise in a field like, say, biology, who has a brilliant idea for a new DNA sequencing chip, but they don't know anything about hardware design.
Okay, I see where you're going with this.
If they could just communicate their vision in their own language, in natural language, it could open up this incredible potential for more direct collaboration with hardware engineers, even if they don't know the first thing about, say, a flip-flop or a floating point unit.
Wow. Okay, that's a powerful thought. So before we get too far into the weeds of how all this might work, let's take a closer look at the HDLs themselves. We keep mentioning Verilog and VHDL. For someone who's new to this world, what are the key things that set these two languages apart? What makes them different?
Okay, so Verilog came on the scene in the mid-'80s, and its syntax, the way the code is written, is similar to the C programming language.
Oh, C. So if you already know C, then Verilog might feel a little bit more familiar.
That's right. VHDL, on the other hand, was developed around the same time by the U.S. Department of Defense.
I'm sensing a theme here. VHDL is going to be a bit more, let's say, rigorous.
It is. It has this very detailed, some might say verbose, syntax with a very strong emphasis on type checking. What this means is that you have to be incredibly precise about the data types you use.
So like integers, floating point numbers, that sort of thing.
Exactly. And how you assign values. Now, this can seem like a bit of a pain, it can make the code longer, but it's also a huge advantage because it helps prevent errors. It's like having this safety net built into the language.
Sure.
And for this reason, it's often the preferred choice for projects where reliability is absolutely paramount. Think aerospace, defense systems, things like that.
Makes sense. So Verilog, a little more like C, maybe easier to pick up if you're coming from a software background.
Yes.
VHDL, super rigorous, great for mission-critical systems.
Right. And then you have System Verilog.
Oh, yeah, we can't forget System Verilog.
Right. That's an extension of Verilog. It has become incredibly popular for a couple of reasons. First, it's really great for hardware verification.
Verification, meaning making absolutely sure that the design does exactly what it's supposed to do, right?
Exactly. Catching errors before you actually build the physical chip. And it's also great for designing really, really large, complex systems on a chip. So CACs, which might include multiple processors, memory, all kinds of peripherals, all integrated together.
Like basically putting an entire computer system onto a single chip.
Precisely. And System Verilog actually incorporates some concepts from object-oriented programming, which makes it even more powerful for managing these super complex designs. So you see, you've got these different languages.
Just like a whole family of HDLs.
Yeah, family of HDLs.
Yeah.
And they each have their strengths, their weaknesses, and they're typically used in different areas for different types of designs.
Okay, that makes sense. Now, when we talk about designing with these HDLs, you often hear about different levels of abstraction. Like you can describe a circuit at a very high level, or you can get down into the nitty-gritty details.
Right.
So can you break down what these different levels are all about?
Imagine you are describing a building, okay? At the highest level, you might just say, it's a place for people to live or work. That's the big picture.
The overall purpose of the building.
Exactly. Now, in HDLs, that's analogous to what we call behavioral modeling. You're describing what a circuit does, its functionality, without getting into the specific hardware components that make it work.
Okay, so that's behavioral modeling. What's next?
The next level down is called register transfer level, or RTL. It's like describing the building in terms of rooms, hallways, and how people move between them.
Okay, so we're getting a little bit more specific.
All right. So in RTL, you are describing how data moves between registers, which are like small storage units within the circuit.
Okay.
And you're describing the operations performed on that data, how it's transformed and manipulated. And all of this is coordinated by a clock signal, which is like the heartbeat of a digital system.
Right.
Now, RTL is really important because it's often the starting point for logic synthesis.
Logic synthesis. That sounds intense.
It is. It's the process of automatically turning that RTL description into a list of actual hardware gates, which are like the fundamental building blocks of a digital circuit.
Okay. So RTL is where we start to get into the actual implementation of the circuit.
Precisely. And below RTL, you have the gate level, where you're specifying the circuit using basic logic circuits, like AND gates or OR gates, not T gates. Think of it like detailing the bricks and mortar of the building.
Okay, so that's gate level. We're getting really specific now.
Right. And at the very lowest level, you have the switch level. That's where you're dealing with individual transistors, the tiny little switches that make up all of these digital circuits. It's like describing the atoms that make up the bricks of the building.
Wow. Okay, that's a lot of levels. But it does help to understand how we can go from a very high-level description of what we want a circuit to do all the way down to the actual physical implementation of that circuit.
Exactly. And, for this whole idea of using NLP in hardware design, RTL is often seen as a sweet spot.
A sweet spot. Why is that?
Because it represents a balance between describing the overall intent of the circuit, the high-level functionality, and also providing enough concrete details to allow for the automated synthesis process to actually create a physical implementation.
Okay, that makes sense. Now, earlier we were talking about how HDLs are really fundamentally different from traditional software languages because they have to deal with the element of time.
That's right.
And also with the fact that hardware is inherently parallel. Lots of different parts of a circuit are happening all at the same time. So how does that actually play out? How do HDLs handle time and concurrency in a way that software languages don't?
This is a key difference. In most software languages, you're describing a series of actions that happen one after another, like step 1, do this, step 2, do that.
It's like following a recipe.
Exactly. Very sequential. But hardware is totally different. Many different parts of a circuit can be active and operating at the same time. All of these signals traveling through wires, different components performing their own tasks, everything happening in parallel. And HDLs are specifically designed to describe this parallelism.
Okay, so I can see how that's going to be very different from programming a computer to do something step by step.
Right. You can actually model how different components behave at the same time, and time itself is actually built into the language. You can specify delays, how circuits react to events over time, all of that. And this temporal aspect, this awareness of time, is absolutely vital for simulation and verification. You have to make sure that everything in your design is operating in sync, that signals are arriving at the right time, that there are no timing violations, that sort of thing.
So it's like orchestrating a very complex, very fast-paced symphony, making sure every instrument comes in at the right moment.
Exactly. That's a great analogy. And, it's a big difference from natural language, where time is often expressed in much more abstract and relative ways. We say things like, I'll do it soon, or it happened a while ago. That's not nearly precise enough for describing how a digital circuit operates.
So already we're starting to see some of the challenges in bridging this gap between natural language and HDLs.
Definitely. Now, let's talk a bit more about some of the structural details of these languages. We said that Verilog has this sort of C-like syntax, and that VHDL is more verbose with strong typing.
Okay.
But what other key differences should we be aware of, like in terms of how the code is actually organized?
Well, both languages use a modular approach to organizing code. In Verilog, these units are called modules. They encapsulate a specific piece of functionality, like a counter or an adder or a memory block. In VHDL, you have entities and architectures. Entities define the external interface of a component, like the inputs and outputs, and architectures describe its internal behavior.
Okay, so both languages are about breaking down a complex design into smaller, more manageable pieces.
Right. Now, in terms of syntax, Verilog tends to be a bit more concise, while VHDL is more explicit. For example, because of VHDL's strong typing, you have to be very specific about the data types you use, and that can make the code a bit longer. On the other hand, Verilog is case-sensitive.
Meaning lowercase and uppercase letters are treated as different things. Exactly. While VHDL is case-insensitive. So those are just a couple of the kind of syntactic quirks that an NLP system would need to be aware of.
Oh, okay, interesting. And you mentioned formal grammars earlier.
Yes.
That sounds like a really important concept when we consider translating from the much looser structure of natural language, right? Like English grammar has all sorts of exceptions and special cases, but these formal grammars seem much stricter. Can you explain why that's so important?
Imagine a game of chess, okay? Every piece has very specific moves it can make, and if you break the rules, your move is illegal. It's not chess anymore.
Okay, I follow you.
Well, HDLs are built on these kinds of very rigid formal grammars. They're often defined using a mathematical notation called Backus-Naur form, or BNF.
Okay, so it's not just about what the code says, but also about how it's structured.
Exactly. These grammars dictate how the different elements of the language can be combined, and they leave very little room for interpretation. It has to be exactly right. Natural language, on the other hand, is super flexible. We bend the rules all the time, and we still understand each other.
Right. Like sometimes I completely butcher a sentence, but you still get what I'm trying to say.
We're good at filling in the gaps.
Yeah.
But an HDL compiler, the software that translates this code into an actual circuit, doesn't have that kind of flexibility.
Okay, so that's a big challenge for NLP, taking this messy, flexible human language and turning it into something that perfectly fits these strict, rigid, formal grammars.
Right, and it's one of the reasons why this whole idea is so difficult and also so fascinating.
Okay, so we've established that these HDLs are a very specific, a very rule-bound, domain-specific language.
Yes.
Now, let's dive into the NLP side of things. What are the core ideas in NLP that could even begin to make this whole thing possible?
At the heart of it is something called semantic analysis. And that means going beyond just the individual words to understand the meaning and the relationships between them. It's about identifying the key entities, their attributes, and the actions being described.
So it's not just about recognizing the words register or adder, but actually understanding what those things represent in the context of a digital circuit.
Precisely. And then you have natural language understanding, or NLU, which takes it a step further. It's about really comprehending the intent, the meaning, and the context behind the language.
Okay, so it's about getting to the heart of what the person is trying to communicate, what they actually want the circuit to do.
Exactly. NLU uses all sorts of techniques, like breaking down text into individual words or punctuation marks, those are called tokens, converting words into numerical representations called embeddings that capture their semantic meaning,
Okay.
identifying named entities like specific hardware components, and figuring out what the user's goal is.
So if I say, I want to create a register to store a 16-bit value, the NLP system needs to understand that register is not just a word, it's a specific type of storage element in hardware. And 16-bit value refers to the size of the data that can be stored in that register.
That's right. And it needs to understand that I want to create a new register, not just access an existing one. NLU is all about extracting that kind of meaning and context. And for NLP to be truly useful in the context of HDLs, it can't just be about matching keywords. It needs this deep understanding of the domain, the world of hardware design.
Okay, that makes sense. So the NLP system has to be hardware aware, so to speak.
Yes, it has to understand the jargon, the concepts, the design principles that hardware engineers use.
Right. And we talked earlier about the semantic gap, this challenge of translating between the way humans describe things, which can be very high level and abstract, and the very precise low-level details needed in an HDL.
Yes.
So how does that play out in this whole NLP for HDLs scenario?
Well, imagine you want to describe, say, a sorting algorithm that you want to implement in hardware. You might say something like, I want to take a list of numbers and arrange them from smallest to largest.
Right.
Now, that's a very high-level description of what you want the circuit to do, the what. But the HDL needs to describe exactly how that sorting is going to happen, the specific hardware operations, the timing, the data flow. That's the how.
Okay, so the NLP system needs to be able to translate from the what to the how.
Precisely. And that's not a simple one-to-one mapping.
Because there might be many different ways to implement the same high-level functionality in hardware.
That's right. You have to make decisions about the algorithms to use, the types of hardware components, the trade-offs between speed and area, and power consumption.
Okay, so bridging that semantic gap is a huge challenge, but it's also where the real power of this technology lies.
Exactly. It's about moving from a very abstract description to a concrete, implementable design.
Now, let's talk about the actual process of generating HDL code from natural language. We've talked about how NLP systems can analyze text and understand its meaning, but how do they actually produce code? What are the techniques involved?
Text generation in NLP is a whole field in itself.
Yeah.
There are several different approaches.
Okay.
One is called a rule-based approach. So you have a set of predefined rules that map specific linguistic patterns in the natural language description to particular HDL constructs. For example, if you see the phrase, create a 4-bit counter, you might have a rule that generates the standard Verilog or VHDL code for a 4-bit counter.
Okay, that's rule-based.
Right. Then there's template-based methods where you have predefined sentence structures or code templates that you fill in with relevant information. But the really exciting stuff, the most powerful stuff, comes from machine learning, especially deep learning models.
So this is where the AI really comes in.
Exactly. These models can learn complex patterns from huge amounts of data. We're talking about recurrent neural networks, RNNs, and even more powerfully, transformer-based models like GPT and BERT. You've probably heard of those.
Oh yeah, GPT, that's the one behind ChatGPT.
That's right. These models are trained on massive data sets of text and code, and they can then generate new text, or in our case, new HDL code, based on a given input.
So you could train a model on a bunch of examples of natural language descriptions of hardware along with the corresponding Verilog or VHDL code, and then let it loose on new descriptions.
That's the idea. And it's a very active area of research right now. So you can imagine being able to describe, say, a simple arithmetic logic unit in English and having the AI generate the initial Verilog code for it.
Okay, that's amazing. But I have to ask, how do we know that the code it generates is actually correct? I mean, HDL code is very sensitive. A small error can have a huge impact on the circuit's behavior.
That's a really important question. And it's one of the biggest challenges in this whole field. The AI model needs to learn not just the syntax of Verilog or VHDL, the way the code is structured, but it also needs to learn the underlying principles of digital logic design. It needs to understand how circuits actually work so that it can produce code that not only compiles without errors, but also implements the desired functionality correctly and efficiently. And of course, the quality of the training data is super important.
So the more examples the AI has to learn from, the better it will be at generating code.
Exactly. The model needs to see a wide variety of descriptions and implementations to learn all the nuances and complexities of translating between natural language and HDL code. And then there's the issue of ambiguity in natural language.
Right, the fact that the same thing can be said in many different ways.
Exactly. The AI needs to be able to figure out what the user really means, even if they express it in a way that's not perfectly clear or precise.
Okay, so there are definitely some hurdles to overcome. Now, we keep mentioning machine learning. It seems like it's at the heart of this whole idea of NLP for HDLs. So can you break down the different types of machine learning that are relevant here?
Okay, so there are a couple of key learning paradigms. One is called supervised learning,
Okay.
and this is where you train a model using labeled data. It's like giving the model a bunch of examples and telling it, this input should produce this output. So in our case, the labeled data could be pairs of natural language descriptions of hardware components and the corresponding HDL code.
So the model learns by example.
Right. It sees what the correct code looks like for a given description, and it tries to learn the patterns or rules that connect the two.
Makes sense.
Then you have unsupervised learning. This is where you give the model a bunch of data, but you don't give it any labels or specific outputs. You just say, go figure out the patterns and structures in this data.
So it's more about discovery and exploration.
Exactly. And this can be really useful for analyzing large collections of existing HDL code to discover things like common coding styles or design patterns, or even potential areas for optimization. And then, of course, you have deep learning.
Which is a kind of subset of machine learning.
Right. Deep learning is all about using these really complex neural network architectures to learn even more sophisticated patterns and relationships in the data. And it's been incredibly successful in NLP because language is all about these complex hierarchical structures and dependencies between words.
And because deep learning models can learn from massive amounts of data.
Precisely. They can sift through tons of text and code and figure out the subtle relationships and rules that govern how language and code are structured and how they work. So deep learning is super promising for tackling the challenges of understanding and generating HDL code from natural language.
Okay, so we have the HDLs, the core ideas of NLP, and the power of machine learning. How do these all come together to actually make interacting with HDLs more intuitive and accessible? Like, what are the practical applications here?
One of the most exciting areas is the development of natural language interfaces for existing HDL tools.
Okay, so instead of having to learn all the arcane commands and syntax of these tools, you could just talk to them in plain English.
Exactly. Imagine being able to say something like, simulate the ALU module with the input values 0101, or what is the critical path delay in this design, or synthesize this design for a specific Xilinx FPGA, optimizing for the smallest possible area.
Wow, that sounds incredibly convenient. Are there any real-world examples of this kind of natural language interface being developed or even used?
There are. There's a lot of research going on in this area. One notable project was called the Hardware Natural Language Interface. It actually explored the idea of implementing NLP capabilities directly in hardware using FPGAs.
Wow, that's meta, using hardware to help design hardware.
Right. And more recently, there's a framework called HDL Copilot that's gaining traction. It uses these large language models to allow engineers to query hardware design kits using natural language.
Design kits, what are those?
These are basically collections of information about specific hardware components and design rules. So instead of having to dig through tons of documentation, engineers can just ask questions like, what are the specifications of this particular standard cell? Or what are the design rules for this particular technology node?
So it's like having a super knowledgeable assistant that can instantly answer your questions about the hardware you're working with.
Exactly. It makes the whole process so much more efficient and accessible. And there are also commercial entities, like Primus AI, that are offering solutions with natural language interfaces for hardware design.
So this is not just a research idea, it's actually starting to become a reality.
That's right.
Now, I can see how this could really benefit engineers who are already familiar with HDLs, but I think it's even more exciting to think about how it could open up the world of hardware design to people who don't have that specialized knowledge.
Absolutely. System architects, software engineers, people from other disciplines who need to understand or interact with hardware, but don't necessarily need to write HDL code themselves.
It's like breaking down the silos between different engineering disciplines.
Exactly. And it could lead to much more effective collaboration and innovation. Imagine a software engineer being able to ask a hardware simulation tool, in plain English, show me the power consumption of this memory block during this particular operation. They wouldn't have to learn the specific commands and scripting languages of that simulation tool.
Right. It would just be a natural conversation.
That's the goal.
Yeah.
And you can imagine using natural language to control simulations in a much more intuitive way, specifying test conditions, monitoring signals, setting breakpoints, analyzing results, all through natural language commands.
That sounds amazing. And what about for hardware synthesis?
The same idea applies. You might say things like, optimize this for the highest possible clock frequency, or target this specific family of FPGAs when you're turning your design into a physical circuit.
It all sounds very elegant and intuitive, but I have to imagine that there are some serious challenges in actually making all of this work reliably.
Definitely. Natural language is full of nuances and ambiguities. Different people might express the same request in very different ways. And an NLP system needs to be robust enough to handle all of that and still accurately map it to the precise parameters and commands that these highly specialized HTL tools require. It's a really tough problem.
It sounds like there needs to be this kind of intermediate translation layer that can take the natural language input and turn it into something that the HDL tools can understand.
Exactly. And that translation layer needs to have a deep understanding of both the natural language and the specific syntax and functionality of the target HDL tool.
Okay, so even interacting with existing tools using natural language is not a trivial task. Now let's step into an even more ambitious area, which is actually designing hardware from scratch using natural language.
That's the ultimate goal, right?
Like, I describe what I want the circuit to do, and the AI just spits out the Verilog or VHDL code for me.
Exactly. It sounds like magic, but there are several approaches being explored. One is that rule-based approach we talked about earlier, where you have these predefined rules that map specific linguistic patterns to HDL constructs.
Okay, so if I say create a 4-bit counter, the system knows what HDL code to generate.
Exactly. But this approach can be quite limited because natural language is so flexible and variable.
Right, there's so many different ways to say the same thing.
That's right. So a more powerful approach is to use machine learning, specifically to fine-tune these large language models on huge data sets of natural language specifications paired with the corresponding HDL code. These models can learn the statistical relationships between the two and generate new code for new unseen specifications.
So the more examples it sees, the better it becomes at understanding the connection between natural language and HDL code.
Exactly. And there are also hybrid approaches that combine rule-based systems for handling the syntax of HDLs with machine learning for understanding the meaning and intent of the natural language input.
Okay, so combining the best of both worlds.
Exactly. And in the long run, the really exciting potential comes from these generative models, like the large language models trained on both natural language and code. They could potentially generate entire HDL implementations directly from natural language descriptions.
So I say, I want a circuit that does this and that, and the AI just writes the code for me.
That's the dream. And it's not entirely science fiction. We're already seeing some early progress in this area.
Are there any specific projects or research efforts that are really pushing this natural language-based hardware design forward?
There are. In academia, there was a project called DAVE-E that used GPT-2, a powerful language model, to translate English descriptions into Verilog code. And there are other research groups exploring how to use LLMs for tasks like automatic code completion and bug detection.
So imagine you're writing HDL code and the AI is suggesting the next line of code or pointing out potential errors.
Exactly. It's like having an AI pair programmer for hardware design. And we're also seeing a growing interest in developing specialized language models that are specifically trained on hardware-related data. So instead of using a general-purpose language model like GPT, which has been trained on all sorts of text, you have a model that really understands the language of hardware design.
That makes sense. It's like having an expert in the field helping you write your code. And what about in industry? Are there any companies actually working on this?
Definitely. We already mentioned HDL Copilot, which is being used to query design kits using natural language. And there are companies like Primus AI that are building commercial solutions with natural language interfaces for hardware design. And even general-purpose AI models like ChatGPT, based on GPT-4, are being experimented with for generating simple hardware implementations.
Wow, so this is happening on multiple fronts, both in research and in industry. That's really exciting. But I have to ask, how good is this automatically generated code? Like, can we really trust it? I've heard about this hallucination problem with AI, where it can produce outputs that look plausible, but are actually wrong.
Right. That's a big concern, especially with code generation. You don't want the AI to create a chip that doesn't work, or even worse, has some hidden security vulnerability. And it's a real challenge. It's hard to guarantee that the code the AI generates is always going to be correct and efficient. There's also the issue of training data.
So if the AI hasn't seen enough examples of good code, it's more likely to make mistakes.
Precisely. And even though these models are getting really good at generating code that's syntactically correct, that adheres to the rules of the language, they might still lack a deep understanding of the underlying hardware design principles.
Hmm.
They might not know how to optimize a circuit for speed or area or power consumption. So there's still a lot of work to be done in terms of improving the accuracy and reliability of this automatically generated code.
So it sounds like we're not quite at the point where I can just describe a complex processor in English and have the AI produce a perfect Verilog implementation. What's a more realistic vision for how this technology might be used in the near future?
I think the near future is all about collaboration. We're going to see human engineers working alongside AI-powered tools. So an engineer might provide high-level specifications and functional requirements in natural language, and the AI can help generate initial drafts of the HDL code, maybe for specific modules or blocks within the overall design. But then the human engineer is still crucial for reviewing that code, refining it, making sure it meets all the design specifications, and rigorously verifying that it works correctly.
So it's not about replacing engineers, but about augmenting their capabilities.
Exactly. It's about letting the AI handle the more tedious and repetitive aspects of coding so that the human engineers can focus on the creative and strategic aspects of design. And it's about making hardware design more accessible to people who don't necessarily have deep HDL expertise.
Okay, that makes a lot of sense. Now let's talk about another area where NLP could have a huge impact: HDL documentation and code understanding. This is often a pain point in hardware development, right? Like the code can be really dense and hard to follow, and the documentation isn't always great.
It's a constant struggle. Good documentation is crucial for understanding, maintaining, and reusing complex hardware designs. But writing it and keeping it up to date can be a real chore. It's often seen as an afterthought, something you do after the code is already written, and that can lead to